Let's first review what we learned yesterday. Yesterday we discussed a lot about this binary hypothesis, right? So this is a binary hypothesis. You see the two Gaussian graph, left and right. So this is a binary hypothesis. So the idea is that the receiver knows that we transmitted binary symbol. So symbol S1 or symbol S2, one of these two. And what we know is that after one of these symbols is transmitted, the noise is added in the channel. So what you received is that maybe S1 plus N is noise, or S2 plus N. So based on that, N is random, and N has this Gaussian statistics. So if you look at the S1 plus N, S1 is a constant. So when you draw the S1 plus N, that corresponds to this Gaussian. Same way, when you draw the S2 plus N, this is going to be the probability density function of S2 plus N. So this picture basically shows you S1 plus N, S2 plus N, all in one picture. This one shows the probability density function of S1 plus N. This is the probability density function of S2 plus N. Okay? And based on this probability density functions, and you know X is the amplitude, right? Based on that, what we are trying to figure out is to calculate this error probability. So this red part is the case when S1 is transmitted, but unfortunately there's a lot of big noise is added. So receiver detected as a S2. So that's an error case, right? So S1, the red part is S1 is transmitted, but we received as S2. This blue area is S2 is actually transmitted, but we received as S1. So both cases are error cases. And we want to find out what is the probability of these errors. Right? That's what we're trying to do. So how to calculate is this equation. This equation tells you how to calculate error probability. And this integration right here, is the integration from minus infinity to alpha. The threshold is alpha. So minus infinity to alpha means all the way from minus infinity to alpha, and integrating to conditional probability of y given S1, which is this one, right? This one, integrating from minus to infinite to alpha. So that corresponds to the red part, right? Same way, this one is integrating from alpha to infinite, and we are integrating over this probability density function. That is this left Gaussian graph, right? So this is going to be the blue part. Okay? That's how to calculate. And each one, we are going to multiply the probability of S1 and probability S2, which corresponds to like weight. So you're multiplying the probability when probability of S1 and probability of S2. So if the S1 and S2 both are transmitted with 50% equally, 50-50, then eventually it will be canceled out. But in this case, it may not be the case, right? Maybe this is 90%, this is 10%. So general equation is like this. As an example, if you assume 50-50 for S1, S2, now then alpha becomes 0. Alpha is a threshold. The optimum threshold is 0. So when you put that in here, then it'll be simplified into this one. That's an example. Okay. These two cases, right? These two are showing you a little bit more detail about this equation, this hypothesis and this equation for these two different cases. We know that there are two different binary schemes, right? Antipodal signaling and orthogonal signaling. We learned these two, right? This binary hypothesis is a general case. any binary signaling, you will see this picture, same picture, because we generalize it as S1, S2, right? But in antipodal signaling, what is S1? Some positive value. And remember that we use this one. That's the energy of bit. The energy of bit, right? And S2 is negative energy of bit. Earlier, when you draw the picture, like this picture, time domain picture, remember that we make it this way as S1, and this level was, we write it this way, right? Remember that? At this time, we basically draw this as a time domain. And the time symbol duration is TB. That's why we divide by TB at that time, right? Right now here, there's no concept of time. Okay, forget the time. When you introduce the time domain, then this is time. But what is the energy inside? The energy is EB. So forget these things. Forget the time domain. I'm not going to talk about time domain here. I'm going to look at just the energy. Bit energy is EB, right? Bit energy is EB. So the amplitude is going to be root square. Just simply think about that way. So S1 is going to be positive signal. S2 is going to be negative amplitude. So that's the antipodal signaling, right? What is orthogonal signal? This is going to be this, S2, 0. That was our example, right? So again, this binary hypothesis is a general case. Because I said S1 and S2. I didn't mention this is a positive, negative, 0. I didn't mention anything, right? I just say this is S1. This is S2. Just general symbol. So any binary system, you draw the same picture. Now let's take an example of antipodal signaling. In this example of antipodal, we're going to see S1 is a positive value, S2 is positive. So now, if you assume antipodal signaling, this one becomes positive root square EB. Now this one becomes negative root square EB, if antipodal is used. Okay? Then what is this Gaussian? F y given S1. What is this Gaussian? That is this one. The mean is root square, positive root square EB. That's what I said here, right? The mean is positive root square EB. Same way, the left Gaussian here, the mean value is minus root square EB. This one. And what is the distance between these two? Remember D, right? D is a very important parameter here. Distance between these two is 2 times root square EB. That is the distance between these two, right? See here? D is 2 times root square EB. That's the case of antipodal signaling. However, what about we use orthogonal signaling? If we use orthogonal signaling, now things are a little bit different. This is the case of antipodal, but if you use the orthogonal signaling, S1 is 2 times of EB, root square. So here is 2 times EB. And S2 is 0. So let's put 0 here. Now then, what is the distance between these two? Distance is going to be this one. Now we have two different schemes give you 2 different distance. So distance is now different. Okay? Distance is different. Which one is a higher distance? This one has a larger distance. Is large distance better or worse? Larger distance is always good. Because make it larger, meaning these two Gaussian graph is getting further away. So it's always good because this area is getting smaller. So simply speaking, when you compare these two, This one is much better. Because D is large, means the error probability is small. So this is better. That's how you compare. And in these two cases, my assumption, in order to make a fair comparison, my assumption is that average bit energy was EB. That's why I select this way, right? My average bit energy is EB for both of them. So I make it same, right? In that way, we make a fair comparison. So bit energy is same, but in this case, you use positive, negative as a two different symbol. In this case, just a positive and 0 as a one symbol, as a symbol signaling. But these two make a big difference because we have a different D. When you have a different D, your BER is going to be different. Okay? Okay, so this is a Q function. We already discussed the Q function, so let me skip the Q function. You need to remember the Q function, okay? Q function is very important. This is a very basic. What you need to remember is the original Q function is defined based on the standard Gaussian. Okay, remember that. However, every time when you see the Gaussian graph, you're going to see non-standard Gaussian. So variance is not going to be 1. So most likely, you always have to use this kind of Q function. So you want to make yourself familiar with this. Okay, always when you have like alpha is a threshold, this is non-standard Gaussian. So most likely you will see like this alpha threshold divided by root square variance of your Gaussian. You'll always see like this. And every time when you have questions about the error probability, your answer is going to be some kind of Q function. Okay? You can get a Q function that's going to be your answer. So remember those things. As we just discussed, distance between two symbols of antipodal signaling is this. In case of orthogonal signals, the distance between these two symbols is going to be a little bit smaller. So put this distance inside the Q function, then eventually you're going to get this Q function as the error probability. So how to get that is that in this case, right, example, this is a simple example. Assumption is that we're going to make these two same as a half. Right? S1 and S2 is transmitted like equal probability. In that case, your threshold, optimum threshold, is going to be the middle point. Exactly the middle point, right? So in this case, if you use antipodal signaling, the S1 is plus root square EB, S2 is the minus root square EB, and S1, S2 is transmitted with the equal power. So therefore, here is plus root square EB. This is minus root square EB. And S1, S2 has an equal power. So therefore, alpha here is going to be 0. Exactly middle point. That's going to be your optimum threshold. So we know that the optimum threshold is going to be 0. However, the distance is D, right? This is D. And optimal threshold here is the middle point, which means that if this is D, the alpha point is going to be like D over 2, half point. So that's why you're integrating this over this graph. So that basically means is that D over 2 here to the infinite, the right side of this equation. So we are integrating blue one. The blue one is this. Okay, we are calculating blue only right now. So blue one is calculated this way. And you will see the D divided by 2 because this is a threshold. That's what we have in the previous slide, right? When you look at the Q function here, you always have a threshold here divided by root 2 square variance. So your threshold will be here all the time, always. So come back here. That's going to be your threshold. Does it make sense? Okay, let me come back to one more time. This lambda is the distance between your middle point and threshold. That's your distance. Okay, that's your distance. So you put distance here. So go to the next slide. What we are trying to do there is that we are trying to calculate this blue region. Blue region. Threshold is this one. And blue region is this graph, right? So we are integrating this graph. Middle point is here. What's the distance between the middle point and threshold? D over 2. That's D over 2. This distance is D over 2, right? So put this here. That's the Q function. This is how to use the Q function. So what I'm saying is that in the previous slide, maybe you can remember this equation. Just remember. Okay? Just memorize it. It's very easy to remember, right? Just memorize it. And then this one is going to be your variance. Whatever variance you have, you just put it here. And what is lambda? This is going to be distance between the middle point and your threshold. That distance is here. Okay? That's how to calculate the Q function. So do the same way. You're going to get this. Same way, you're going to get this. However, D, in this case, in antipodal case, is this, right? This is D. So put this D right here. You're going to get this equation. So that particular equation here, Q function D divided by 2 root square variance, this equation is general equation. This equation is not for antipodal. This is for everything, basically, right? And if you use antipodal, you have your own D, antipodal signaling D. Put that here, you get this. What about for orthogonal? Orthogonal has a different D, another different value, right? Put this D again here, because this is general equation. Put this D here now, you're going to get this. Now let's compare these two. Which one has a smaller probability? Again, that's going back to question. Which one has a smaller probability? This one is a smaller probability because this one is like 2. This one is going to be 1. Okay? So this one has a smaller probability. So these two, when you compare these two, which one has a smaller probability? This one is a smaller probability. Why is that? Because, as I said, D is larger. In this case, D is larger, right? So error probability smaller. It's actually very easy to get. Once you remember the Q function and how to use this Q function, right? Then just put this distance here and variance here. That's going to be your answer. That's your probability, error probability. And that's what we did. Exactly, that's what we did. Okay, so those two. We already discussed this one, right? So this is the case for the optimum threshold And the reason that we need to think about the optimum threshold, alpha, is because that sometimes S1 and S2 are not equally transmitted. This is generally this is true, but in some other time, in some cases, this is not equal. Maybe this is like 80%, this is a 20%. That's possible, right? So if that's the case, then we starting from the original equation, come back here all the way, and we're gonna come to conclusion. That is the conclusion. And this is all the process how to get this one. But anyway, the conclusion is this. So this is the equation how to calculate the optimum threshold. So when you have this case, for example, then S1 is gonna be this, that's 80%. This is 20%. So you have this one. Put these two numbers here, right? Then this is gonna be your optimum threshold. So, and use that optimum threshold, alpha here. And we also need to know about the distance d. In order to find out the distance d, first you have to decide what signaling you want to use. Do you want to use antipodal signaling, or do you want to use orthogonal signaling, or do you want to use some other things? So depending on which signaling you use, now S1 and S2 will be decided. Okay? Once you decide S1 and S2, now we know the D, right? And once you know these two, now we know the alpha. So once we know the alpha and D, we can calculate error probability. Okay? That's the whole process. Moving on to next slide. This slide is an extension of the previous one. So far, what we learned is a binary case. Maybe S1 and S2, only two cases. So that's a binary case. Now what we are talking about here is the general case, Emory. We call this one as Emory. Emory. And M can be 2. In that case, it's called a binary. If M is 2, we read that as a binary. Bin means 2, right? Bin. In English, bin, right? Try means 3, something like that, right? So bin, put that here, binary. But generally, we call this one as an Emory, M. M can be any value. This particular example shows you the case of M equal to 4. M is 4. 4. Okay? And this is an also example of PAM. You know PAM, in PAM, your information is in the amplitude. That's PAM, right? Your information is in amplitude. So if you have a 4 symbols, like this one, S1 to S4, 4 symbols, your information is in the amplitude. So which means that you need to have a 4 different amplitude. Like this, right? You see that 4 different amplitude. Like this is a 3A, A, minus 3A. 4 different amplitude. So that's a 4 Emory PAM. For example, right? Maybe this is an example that you transmitted this kind of signals in time. Like a 3A, minus 3A, minus A, 3A, minus A, something like this, right? This isn't just an example. And when you plot this in the constellation plot, you can see this kind of constellation plot. And in this case, in this constellation plot, it just shows you amplitude. There's no phase here because we are not using phase. This PAM needs only amplitude, right? We are looking at only amplitude in this modulation. So phase doesn't matter, right? Phase doesn't matter. So we didn't plot the phase here. We only plot the amplitude. But anyway, in this case, we have 4 different amplitudes. And what you can also notice is that the distance between these two and distance between these two and these two is same. Distance between the neighboring symbols is the same. 2, 2, 2. 2D, 2D, 2D. Like that, right? So that's an example of Emory, PAM, when m equal to 4. Right? Okay, now in that case, okay, let's go back here one more time. So now in that case, what do you think the value of A here? I just make an A, but I want to calculate the A. This is a 3A, A, minus 3A, but I want to calculate the A. And what I want to do is that I want to make my average bit energy equals to EB. Okay, no, let me change it here. My average symbol energy is ES. Okay, I'll tell you what that means. This is not bit energy. This is symbol energy. So I want to make my average symbol energy as ES. So which means that when you see this, right, this symbol has more energy than this, right? This one's smaller energy. This is more energy. But now let's assume that this is those symbols are transmitted with equal probability, right? 25% this one, 25% this one, right? All these four different symbols are transmitted with equal probability. You can now calculate the average symbol energy to be ES. You can do that. How do you calculate that? Maybe we can go back to the previous binary case. In binary case, orthogonal case, how did you calculate the average energy, bit energy? So let's say A. How do you calculate the A? This is S1, S2. What I want to do is that my average bit energy, I want to put it into EB. So how did you calculate the A at that time? TB. How to calculate that at that time was integration from 0 to TB and A square dt. This one gives you energy in this symbol, in this bit. You can do the same way for this particular symbol here, but this particular symbol is actually 0. So when you add these two, and each one you want to multiply the probability of this, but in this case both of them is half, half. Now this whole thing needs to be EB. So this is the equation, right? That's the equation for to calculate the average energy, bit energy. This is the energy for this bit. This is the energy for this bit. When you add these two, put that together, the total energy should be EB. So when you calculate this, now you're going to get A. Okay? A is going to be some number, like root square 2 EB, something like this, right? So this is how to calculate. What about this one? How do you calculate A? You can do the same way, right? You can do the same way. Exactly the same way. So the first one, how do you calculate it? In this case, actually, you can see the time is Ts. This is Ts. So you're integrating from 0 to Ts. I'm talking about this one. The first symbol, actually, the probability is 1 over 4 times 0 to Ts. And amplitude of this is 3A. So you are integrating 3a square dt. That's for S1. Same thing for S2. Same for S3, same for S4, right? Eventually that equals to ES. So that's in the next slide. You don't have to write it. That's on the next slide. You don't have to write it. So that's in here. This is what I'm talking about. Right? You're going to do this way. So that's what you're calculating. So this is the energy for the S1. This is the energy for S2. Energy for S3, energy for S4. But each symbol has a different energy. So you are putting all together, and each one is transmitted with equal power, equal probability, 1/4. Multiply that and add it all together. Then eventually this will need to be same as my average symbol energy. So you can simply solve this equation, right? Put that all together, so solve it. Eventually you're going to get A to be this value. So once you get the A to be ES divided by 5 root square, now you're going to go back and put that A here. So this is going to be now ES divided by 4 root square. This one is like minus 3 ES divided by 5. Something like this, right? So that's how to calculate the A. And what is the condition for this A? My condition is I want to make this. I want to make my average symbol energy is going to be ES. That's what I want to do. And in order to do that, you need to get the A to be that value. Okay. Now, what about that the probability of those symbols are not same? So, for example, right, S1 is transmitted like 50%. This is 20%, maybe 10%, 20. If this is the case, like unequal transmission, right? Unequal transmission, how do you calculate the A? Now A is going to be different. How do you calculate the A? This way. This way. It's actually same, right? Same. Only difference is that instead of 1/4, I just multiplied its own probability. Like a 50%, this is going to be half. Like a 20%, this is 1/5. Something like this, right? You just multiply your own probability. This is going to be the energy for S1, energy for S2, same way. And eventually that needs to be ES, same way. You can calculate the A like this way. So the how to calculate is same. So once you do this, now we get the A. Then we can complete this picture by put the correct A like that. And now you get the picture of S1 to S4. Okay, that was the case of PAM. Okay. Now let's look at another case of memory, but M is 4. Even in the binary case, we looked at two different signaling, right? Orthogonal signaling, antipodal signaling. But both of them is still binary case. Binary signaling, you have two different signaling, right? In memory signaling, memory PAM, memory signaling, when M equal to 4, we can also think about several different ways. This way looks almost the same as antipodal signaling, right? Because it's like a plus minus, like a minus plus. It looks like antipodal, kind of, right? What about this? Now what you see here is 4 different signals, S1 to S4. This signal actually is orthogonal way. This is orthogonal. From here to here, only this one has on, off, off, off. For the second part, off, on, off, off. Something like this, right? So it's almost same as the orthogonal signaling. But now we have 4 symbols. What about this? This signaling is also orthogonal. Also orthogonal signaling. How do you know? It's very easy to see it, right? How do you know this is orthogonal signaling? Easiest way to check is let's do inner product. How do you write inner product? Like that. This is inner product, okay? So let's do inner product between S1 and S2. How do you do that? How do you do that? Let's just multiply these two and add it. Now this is like 1, 1, 1, 1, for example, right? Like this one is a 1, 1, minus 1, minus 1. Something like this, right? This is like 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1. Something like this. So let's multiply these two and add that. Once you do that, right? 1, 1 becomes 1. 1 times 1, 1. Minus 1 times 1, minus 1. Minus 1, 1, minus 1. So add that together, becomes 0. Same thing for these two. When you multiply these two, like a bit to bit, right? This bit, this one, this one, this one, this one, this one, this one. Bit to bit, and then add it together, 0. These two, 0. These two, 0. Any of these two will give you 0. That means orthogonal. Same thing for this, right? Same thing for this. Why? This is like 1, 0, 0, 0. 0, 1, 0, 0. Let's do the same way. When you multiply, you get 0. Same thing. 0, 0. Any one, you get 0, right? So that's why we see that this is like orthogonal signaling in case of m equal to 4. Okay, so let's move on. We already learned this correlation type demodulator and matched filter, right? We already learned that. So when we learn this correlation-based demodulator and matched filter, earlier we used the binary signaling, orthogonal or antipodal, right? For binary signaling, we already learned that. What about we use Emory? What about we use Emory signal? In that case, we are going to have m number of correlators and m matched filters. That's as simple as that, right? In case of binary, we have 2 of them. We have 2 matched filters, right? Because there are only 2 symbols. Okay, let me remind you one more time. What is the correlation type? What's the idea? The idea is that we know that only the possibility is S1 to S1, S2, S1, S1, S2, dot, 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 Sm. We know that there are m different symbols available. Transmitter transmits one of these, maybe S5, maybe S2, something like this, right? Now what we do is that we receive that with the noise, and we're going to compare it. Which one looks more similar? That's correlation, right? Maybe the receive symbol looks more close, more correlated with S1, and looks much more close to S2. Basically, that's what we do, right? Just trying to find which one looks closer. That's correlation, right? So even for Emory, you can do the same thing. You already have the perfect signaling, m different perfect signaling, Now you just compare which one has a higher correlation, and pick the higher correlation one. That's as simple as that. Same thing for match filter. Okay, we already know the perfect signal. Maybe S1, S2, Sm. Now what you want to do is that for each filter, each match filter, you're going to flip this S1, right, and wait. Same thing, S2, you already know S2, and flip it and wait. Okay, and then once you get the R, now you put this R into the correlator, you just do correlation, right? Then this one is already flipped. And when you do correlation, flip it and correlate, right? And that's exactly same as your correlation. So when you do convolution, flip and the convolution, right? So this one, same thing. Eventually, once you do that, and you're going to do sampling at the right time, you get all values, and each value shows you the correlation. And you're going to pick the largest one. That's your answer. So exactly same idea for binary can be applied here. So memory, nothing different. It's almost same thing. Okay. Once you use that memory signaling, eventually you need to calculate the error rate. In the binary case, right? Again, our final goal is to look at the performance. When you use a binary signaling, like antipodal or orthogonal, how much error do you get? And what is the probability of error? That's eventually what we need to find out. And you're going to do the same thing here. When you use the 4 symbols, like M equal 4, that's an memory case, right? You also can be calculating a error probability. But in this case, since we have 4 different symbols, now you have a many different error probability. When you have a 2, right? There's only 2 cases. Like S1 is transmitted, but S2 is received. Or S2 is transmitted, S1 is received. There are only 2 cases, right? But when you have 4 symbols, there are many cases. Like you transmit S1, and you receive a S2, that's error. You receive as S3, again error. Maybe you receive as S4, again error. How about S2 is transmitted? Then S1 received, S3, S4 received, all those are error. So there are many different error cases, right? Many different error. So that's what we listed here. S1 transmitted, S2 received. Okay, that's what that means. S4 is transmitted, S2 is received. All of these are error cases. All of these things, all of these things, all of these. All of them are error cases. So what's going to be eventually the error probability? You're going to calculate each of these error probability, all of them, and add it all together. That's going to be your eventually error probability. So there are so many of them, right? However, in this case, there are so many of the error cases, but you don't have to calculate all of them because there are only a couple of different types. When you look at here, right? Let's take a look at this one. S1 is transmitted, but S2 is received. In that case, S1 is transmitted, but S2 is received. So that is this probability right here. What about this? S4 is transmitted, S3 is received. So S4 here, but S3 is received. That's this probability. This probability is the same if you use this assumption. So let's say S1 to S4 are transmitted with equal power. Okay, that's assumption. If you make this assumption, now what you can see is that this whole thing you can see as a mirror, like a symmetric. So whatever you have here, this value will be same. So these two are same. So you don't have to calculate both of them. Just calculate one. This one is going to be same because it's equal power. It's like a symmetric. What about this? S1 is transmitted, but S3 is received. So S1 is transmitted, but you receive the S3. So which one is the probability then? This is actually very, very small. So it's a little bit difficult to visualize here. But let me make it a little bit bigger. Bigger here. Here's S1, S2, S3. S1 is Gaussian like this. S2 is Gaussian like this. S3 is again Gaussian like this. So probability that S1 is transmitted, but I received as S3, that's of course an error. But that error is like S1 is transmitted, but S3 is received. So this is the error. This is the error. What about S1, S2? S1 is transmitted, but S2 is received. So which area is that? This is the area. So now what you can see is that we're going to make a region. In this case, we have one threshold. Second threshold, we have three different thresholds. In binary case, we only have one threshold, right? But when you have four symbols, now we have three threshold. Three threshold. From this threshold all the way to the right, that's going to be the region for S1. Between this and this, that's for S2. Between this to that, that's the region for S3. All of the leftmost area, that's for S4. Now the problem is S1 is transmitted, but we receive the S2. Meaning that S1 is transmitted, so we are going to use this graph. So what is the probability that this graph goes into this region? So that region here is going to be this probability. S1 is transmitted, but we received as S2. So that goes into S2. S1 is transmitted, but we receive the S3. That means S1 is transmitted, but we receive as a S3. This region. It's so tiny, but there is a little bit here. Because this one goes infinite, right? We have a very small one here. So that is this probability here. And S1 is transmitted, and S4 can be received, right? This is very unlikely, but still it can happen. That means S1 is transmitted, but since this one goes infinite, there is a little bit of probability here. Okay, that's S1 to S4. Right? So that's why we have only three different cases. You don't have to calculate all of them because we know that this one is same as this. So you calculate this one and use the same value for this. Same thing. When you calculate this one, we know that this one is the same. So just calculate one, and for the other one, use the same value. Right? So you just calculate a couple of them, and then put them all together. So that's how to calculate the bit error rate. Okay. Now then, let's take a look at here. Okay, hold on. This is not the right one. Actually, have some more things. So that's what I talk about here, right? So this is the case when you have a symbol error. So we have a S1 transmitted, but S2 is received. So since you are transmitting S1, now we are using this graph. But since we received the S2, we are integrating between these two areas. So how do you calculate this? This is again Gaussian. So anyway, this is a Q function. Okay? Then let me ask you again. How do you calculate this Gaussian, this area? Let's think about this way. How to calculate this area is going to be you flip it. You flip it and make it this way. Once you have that, then we already know the answer. That's going to be this. That's our error probability. This one now looks a little bit different. A little bit different. That one looks like this. We are integrating between minus lambda 2 to minus lambda 1. It's not like minus infinite to lambda. We are integrating from minus lambda 2 to minus lambda 1. So how do you calculate? First of all, we have to flip it. Okay, so let's flip it like that. So lambda 1 here, lambda 2. So how do you calculate it? Yeah, it's very easy, right? First, lambda 1 to infinite minus lambda 2 to infinite. Then you get this. That's simple, right? So that's why this one, you are getting two different Q functions and subtract it like this. That's as simple as that. Q function minus another Q function. That's going to be this area. This area. Right? It's very simple. That's it. Same thing for probability S1 to S3. You can do the same way, right? Only difference is that now the threshold is different. This probability S1 to S2, you're going to use these two thresholds. Because we received as S2, which means that your received symbol is within this range. So your received symbol is somewhere here. That's why we are integrating between this threshold to that threshold. That's what we do here in this picture. This threshold to this threshold. This case, S1 is transmitted, but S3 is received. Exactly the same way. In this case, you are going to use this threshold to this threshold because you received the S3. So now the threshold value is different. All of the equation looks exactly the same. So instead of 3D, 5D, you're going to use different threshold, different value. Everything else is almost the same. Okay? Okay. So now let's move on here. So based on this technique, you can calculate the average probability for all different cases. Now this slide shows you examples. First of all, let's see. Error probability for S1 to S2. S1 is here, S2 is here. So we are integrating between lambda 1 to lambda 2 because that's the region for S2. So we are integrating between that. And as we said, it's going to be Q function minus another Q function. Same for S1 to S3. We are integrating between these two now because that's the region for S3. right? This is 3, right? Lambda 3, yeah. Lambda 3 to lambda 2, so between these two regions. So you are integrating the same way, Q function minus another Q function. Difference between these two is that your threshold value is now different, right? That's only difference. Same thing for this. What about this one? S1 is transmitted, but you receive the S4. In that case, what is the region for S4? S4 has the region minus infinite to this. So in this case, it's going to be like just one Q function. Right? Just one. Minus infinite to lambda 3. So it's just one Q function. Same thing for this. S2 to S4. S4 has that region, minus infinite to lambda 3. So you're going to get this function. So we have 6 different types. Right? 6 different the cases of error. There are more cases, but the other cases looks same as one of these. So you can just copy it and use the same way. And put this all together, that's going to be your average bit error rate, average symbol error rate. Okay. Now what I need to talk about is this one. So yesterday I talked about the bit energy, average bit energy. I mentioned bit. I always say bit, but today I never say bit. I always say symbol. So now, what's the difference between bit and symbol? And as you see here, sometimes we are doing conversion. You have a bit, change it to symbol, or symbol, change it back to bit. What's the difference between these two? Original information starts from bits. We have a bit sequence. That is the original information. Okay? In digital communication, everything starts from bit. And bit eventually needs to be changed to symbol before transmission. So whatever transmitted here is always symbol. Bit is never transmitted. What is transmitting is symbol. Every time, symbol is transmitted. So therefore, eventually your information is bits, but the transmitted information is symbol. So somehow you have to change the bits to symbol. That's what happened at the transmitter. Receiver receives the symbol and change it back to bits. So bit to symbol conversion is done in transmitter. Receiver symbol to bit conversion. That's a part of the modulation. We learn modulations, right? We are still learning modulations. And one of the things you need to do in modulation is conversion. Bit to symbol conversion. So once you do the modulation, bit, change it to symbol. What about this is a modulation, right? Binary PAM. PAM is a modulation. So this is a binary PAM modulation. So that's why we know that 1, 0 is a bit, 1 or 0. Using binary antipodal signaling, that's a modulation. Once you do that, bit is input. What is your output? S1 or S2. And antipodal signaling, S1 is like plus this, S2 is minus this. This is what is transmitted. but original information 0 or 1. So this is a conversion. We have already done that. We are already doing the conversion. But this is the case of binary case. Okay, this is the binary case. In binary case, we have only one bit, one symbol. I mean, the bit to symbol mapping is 1 to 1. Like a 0, maybe S1. 1 is mapped to S2. It's like 1 to 1 mapping because there is only 2 bits, 2 symbols. In Emory case, now it's different. Not binary, but let's say Emory and m equal to 4 as an example. Now we have 4 different symbols. When m equal to 4, right? 4, we have 4 symbols. Okay? But you have only 0, 1. Do you have a 2 and 3 in bits? No. Bit is always 0 or 1, right? Only 2. Then how do you do mapping? That's the question. We need to do mapping between bits and symbols. But how do you do mapping? We have only 2 in bits. So that's why we cannot do mapping, right? And how to map between bits to symbol is that now we collect 2 bits. 0, 0, 0, 1, 1, 0, 1, 1. Because we have 4 symbols, you need 2 bits. In this case, 2-bit is a group. 2-bit is always a small group. You are not going to separate. 2-bit is like 1. Okay, 2-bit is 1. So we have 4 different choices, right? So once you have these 4, now you can do one-to-one mapping. One-to-one mapping, right? For example, 0, 0 corresponds to S1. 0, 1, S2. 1, 0, S3. 1, 1, S4. That's one example. Maybe you can do another way. 0, 0, I want to do S4. That's okay. 0, 1, S2. That's okay. Okay? So you can do one-to-one mapping. That's again what happened in the modulation. In this case, it's going to be Emory modulation. And what we are explaining here is bit to symbol mapping. That is going to be the mapping. Bits to symbol mapping. Like this one is one example. Or if you like, you can do this mapping. That's fine. Okay, that's fine. That's the mapping. So in this case, S1 is mapped to 0, 0. 0, 1 is mapped to S2. 1, 0, S3. 1, 1, S4. That's my mapping. You can do another way. However, we have to remember one thing here. Here's a question, right? You can do whatever mapping you can do. But is this a good mapping? There are many different ways mapping. But there's one rule in mapping. This is not a good mapping. Why is that? Okay, that's what we need to remember here. Think about here. S1 is here. This is still the hypothesis graph, right? S1 corresponds to here. S2 here, S3 here, S4 here. Now, we like to think about the average, the error probability. Let's say you transmit S1, and there is an error. Okay, there is an error. Which one has a higher probability? When you receive an error, you receive the error, so you are not received S1. You transmit S1, you receive the same S1, that's not error, right? You have an error. So, which means that you received this one, this one, this one. Maybe one of these 3. But which one has the higher probability as received? S2, right? When S1 is transmitted, and if there's an error, most likely that's going to be S2. S3, S4, very unlikely. Because S1 is transmitted and noise is added, and you receive the S4, that means this noise is like a minus 100. Something like that, right? Only in that case you receive S4. But this is very, very unlikely, right? So most likely, probability point of view, when you transmit S1, S2 is received symbol when you have an error. So this one, P, S1 to S2, P, S1 to S3, probability S1 to S4. Which one has a higher probability? This one has the highest probability. This one is so small. This one is almost nothing. Okay? Right? Same thing for S2. Let's say S2 is transmitted. Most likely, when you have an error, you receive the S2, S1, or S3. Something like this, right? Okay, in that case, now let's come back here. Now let's say, now I transmitted S1. This one, right? As I said, when you have an error, most likely I receive the S2. So I receive the S2. Just the example. Let's say I transmit S1, but I receive the S2. So that was error. But we don't know that's error, right? Receiver doesn't know if that is error. Because receive 2 just received some value here and just decode it, and that turns out to be S2. So we don't know that's an error at the receiver. So now S2, when S2 is received, we are going to decode it back to bits. Originally at the transmitter, we have 0, 0 as an information. At the transmitter, we convert 0, 0 into S1 based on this mapping and transmit it over the air. Now noise is added, noise, and we receive that as S2. Receiver will convert back to bits. Eventually we recover this, right? Because originally it was bits. Change it to symbol. Transmit in the channel. In the channel we have a noise. We receive symbol at the receiver. Eventually change it back to bits, right? So now let's take a look at the bits. We transmitted bits. This one was original bits. Now we recovered the bits, but it was 0, 1. So how many bits do you have? 1 bit error. 1 symbol error means 1 bit error. 1 bit error. That's good, actually. 1 bit error is the best case. So that's good. Now let's think about different case. In this time, now I transmitted S2. Transmitter originally have 0, 1. Okay, now convert to S2 and transmit in the air, in the channel. Again, noise is added. We receive as S3. Okay, receiver now converts back to bits, same way. Now we recover bits. So original information was this. Now recover back to bits, we get this. How many bit errors? 2 bits. This case, 2-bit errors. So what I'm saying here is that sometimes you get 1-bit error, sometimes you get 2-bit errors. Okay? Sometimes. So 2-bit error is a worse, right? Worst case. So that's why this is not a good mapping. We want to avoid this case. Okay? Yeah. Okay, let's continue next time.